Neurips 2024, part 11. Today's paper is about pose estimation. The actual title is Vision Foundation Models for Pose Estimation. Pieter Abbeel et al., UC Berkeley and China University of Hong Kong. Let me talk about the problem first and then discuss the paper. So the problem of pose estimation is very common particularly in robotics, to some extent also in virtual reality and augmented reality. So you see an object and you want to understand how does it relate to the real world, right? You see a chair and you want to know where is up, where is down, what's the function of the thing potentially. And in 4D, so if you add the time dimension to it, you also want to have a bit of a sense how it's going to be, how it's going to behave in the next few instances. In other words, maybe in the next few seconds. For that, you need to understand its pose. So if you take a picture, so if your self-driving car takes an image, in this instance, in T0, it sees a dog. It helps to understand what the dog's front and back is. It helps to understand where the dog comes from and then predict where it's going to go. So that's a very canonical example of pose estimation. But you can have a glass, and understanding where it's up and down would definitely help you in terms of filling the glass with water. Let's just sort of lean back for a second and just try to understand. A robot has no idea about spatial relationships, such as, for example, the glass is on the table, right? We discussed this actually in the Percy Liang paper. It was the number 9 of the Neurips presentations, embodied agent interface, benchmarking LLMs for embodied decision making. The problem there was that you can use large language models to tell a robot what to do. For example, fill the glass with water. Like it understands that, but then it might actually not understand that the glass is upside down and then just fill it up, right? So this is something, a canonical example of a pose estimation. Imagine you take a glass and you put it on the table, but you turn it upside down. Well, does the robot really understand where it's up and down in the glass? Or imagine you put a glass just right under a table and then you tell the robot, go fill the glass. It might pour from top and then not be able to reach the glass because the table's in between the glass and the robot. So that's, I think, why we need pose estimation. Now let's talk about the techniques. What the authors are suggesting here is, in a nutshell, a better estimation of what we're seeing, and then an extrapolation from what we're seeing in 2D into 3D using what's called NOCS, which is a normalized coordinate system. That is, think about it this way. You see a glass, and then you categorize, okay, every glass gets compressed into a cube with a coordinate system. Whether it's a wine glass, whether it's whatever glass, it's going to be compressed, of course, with keeping the relationships of the actual geometry. I'm not 100% familiar with the actual techniques, I think, but this is one of the innovations here, that you're using a simplification, right? Because you don't have to be 100% correct in terms of, millimeter precision of how you represent the glass. But what you want to do is have a sort of big picture sense for the shape of the object based on its category. And then you can create a coordinate system, which is normalized. That's what the NOCS means. And from there, estimate the pose. Before you even do that, there's another technique called point cloud transformer. So that comes even before, which is, so you take an image, you create a point cloud, and you transform that. You use a transformer, which is the same idea like in any other transformer. You have a generalized model which has been pre-trained on using point clouds and turning them into shapes. So like every other transformer, it's a compressed representation of knowledge about shapes. So glasses, dogs, cars, all kinds of objects are being compressed, and then you use the NOCS to create a coordinate system. And then what you achieve with that is really fundamentally two things, right? One is we're pretty good at identifying what we're seeing, even if we haven't been trained on this particular thing. So if we haven't seen this particular wine glass, we can still, with high fidelity, assume that it is a wine glass, and more importantly, with high fidelity, assume it's pose estimation, because we have an NOCS, normalized coordinate system, that is translated out of the picture that we've seen after we've done the point cloud transformer, and therefore we have a pretty good representation of its point estimation. One thing I also want to mention, which is interesting here, they're using synthetic data to train the model. So they're using the foundation model, which is the the pre-trained representation of knowledge about shapes and point clouds and coordinate systems, and based on categories. You're using that as a fixed, so you freeze that and then you fine-tune the model with synthetic data. So what they did is they created synthetic data. So they take, let's say, a glass, they take several instances of the actual glass, the ground truth, and use one of them as identification and the others as okay, it's what if I turn it right, if I turn it upside down, and that's what they use to fine-tune the model. And that to me seems also a pretty sort of innovative way. So three big innovations in the paper. One is the point cloud transformer, second is the normalized coordinate system, and third is the synthetic data for training and for fine-tuning. Those three systems have been used to engineer this pose estimator, which then hopefully allows us to do a general pose estimation. This is the key, right? If I have a humanoid robot going around the factory floor, I want to understand how these tools are relating themselves to each other, to the geometry, and potentially also with the physics, which will be the Cumming-Hebb paper in number 10 of our conversation. So physically realistic 3D representations from 2D images. They are not doing this here. So this paper is not doing any physics, but you could see the connection, right, between the actually number 9, number 10, and number 11. So number 9 is trying to understand the semantics of objects. So a glass is upside down, so we have to turn it around in order to pour water in it. And then we have the Cumming-Hebb paper, which is we understand the physics. So if the glass slips down, it's going to fall based on gravity and it's on its deformation. And that is, of course, related to the pose estimation, because we will understand the pose of the glass once it has fallen down from the table. So to summarize, I think pose estimation is an undervalued problem. It's one of those things that that's what I like about Pieter Abbeel's work and in general the work at Berkeley, which is they're really working on foundations for robotics. They're trying to build a solid foundation of generalized models that then can be used for fine-tuning and solving certain problems, in this case pose estimation, which is a canonical problem in robotics. In order to understand semantics, you have to understand pose, right? You can't fill a glass with water if you don't understand that the glass is upside down, that you have to turn the glass first. And those are the kinds of problems that Percy Liang in his paper et al. have identified. You then have to understand the physics. And if you don't understand the physics, at least you want to understand geometry, which is what the people here are doing. So you want to use point cloud transformers and normalized coordinate systems in order to have a good sense for how the object that you're seeing, what it is, what category it belongs to, and how it might behave. Thank you.